Two cosmological mysteries continue to fascinate scientists and science enthusiasts alike. The first is understanding in detail how the universe came into existence. The second is the nature of dark matter, a substance which is thought to be far more prevalent than all the stars and galaxies in the universe. A recent paper explores a possible intricate connection between these two phenomena and proposes that the beginning of the universe included not one, but two Big Bangs. To understand the implications of this interesting new idea, we must first consider the prevailing understanding of both the Big Bang and dark matter. If you think of the universe as a cup of coffee, as far as we know, the coffee itself will remind us of the dark energy that makes up almost 70% of the universe. The milk we will add will remind us of dark matter. And the sugar we will put in will remind us of the matter that we see, and that makes up 5% of the universe. For those who don't know the subject, we say dark matter and dark energy because we have no idea about them and cannot see them. Naturally, you might say, how can you compare it to milk? But that's a pointless question, as it doesn't mean that dark matter will be dark. First of all we know about dark matter is that it has a very strong gravitational effects and does not interact with the objects we see in the universe except by gravity. If you ask why we say this, there are two reasons. The first reason is the mass inconsistency in galaxy clusters. Galaxy clusters are formed by the coexistence of galaxies in groups. Just as the planets in our solar system are held together by a force, there is a force that holds galaxies together. This indicates that there are packets of energy in the spaces between galaxies that need to be taken seriously and are connected by invisible filaments. But mass calculations of galaxy clusters apparently show that these clusters shouldn't exist, that they shouldn't stay together, or even move away from each other very quickly. Because of this problem in the early 20th century, astronomers wanted to focus on a single galaxy to better understand the situation, the Andromeda Galaxy. It is both a galaxy known for its proximity to us and a spiral galaxy. Spiral is important because almost most galaxies in the universe are spirals. Naturally, any conclusion to be drawn from this would constitute an induction that could be applied to the entire universe. And second reason, the observations were surprising, because according to calculations, the rotation speed of the galaxy should be like the one on the right. However, the observations were that the rotation of the galaxy was much faster. That's why it was said that there is something we don't see. And this thing is not only gravitationally affecting visible objects, but also allowing them to defy physics as we know it. Therefore, the discrepancy between the expected and observed rotation curves is explained by adding a halo of dark matter surrounding the galaxy. Despite numerous searches, no dark matter particles have yet been found. Quite a few candidates for dark matter have been proposed, from axions to sterile neutrinos to even more bizarre and mysterious candidates like weakly interacting massive particles or WIMPs, which had been a favorite of string theorists. What's more, a recent study said dark photons could also be good candidates. But the problem is that even though we had concrete observations, we couldn't say, yes, dark matter, we're sure, for a single particle. Don't be fooled by what I call concrete observation. Yes, we are observing something that is not within our formulas, but that doesn't mean we need an external phenomenon. Despite this, those who look definitively at such a phenomenon, especially those who have published their articles in respected journals of the scientific community, have always continued their research by looking at dark matter as something that is definitely. We have many models, but two of them stand out. One is the LCDM model, and the other is Modified Newtonian Dynamics, or MOND for short. The LCDM model is referred to as the standard model of Big Bang cosmology, as it combines the cosmological constant lambda, which Einstein called my biggest blunder, and the dark matter-related CDM. It is a very imaginary model in the sense of trying to find the unknown by taking the unknown into account when there are so many unknowns. In short, while extraordinary claims require extraordinary evidence, we have added these claims to the models. However, like there are those who drink coffee without sugar and milk, those who looked at it from a more realistic point of view said, why do we add imaginary things to our models that we know nothing about? And formulas were developed that challenged this model. The most notable is MOND. The idea of MOND was inspired by the rotation of galaxies. First published in 1983 by Israeli physicist Mordechai Milgram, the hypothesis's original motivation was to explain why the velocities of stars in galaxies were observed to be larger than expected based on Newtonian mechanics. MOND proposes to alter the acceleration of gravity depending on how strong the acceleration is. For large accelerations, which apply to anything within the solar system, the theory is the same as Newton's, which means that the force on an object is proportional to its acceleration. Force is equal to mass times acceleration. This is summarized in the following equation, F equals ma. For very tiny accelerations, however, the force is proportional to more like the square of the acceleration. What this means is that for objects that are very distant from a galactic center, the force on them is independent of the distance, and thus their rotational curve is smooth. Of course, just adding a small term to Newton's gravity means that you also have to modify Einstein's equations as well. So MOND has been generalized in various ways, such as équal, a theory of gravity based on modified Newtonian dynamics, MOND, but using a Lagrangian, which stands for a quadratic Lagrangian. Just like the lambda cold dark matter model, équal could explain these inconsistencies in the universe and does not need phenomena such as dark matter or dark energy to do so. What makes things even more interesting is that a recent study that has already been done supports this theory. Indeed, according to the study, the MOND theory was almost perfectly compatible with the observed and simulated galactic spin curves. The research made us all ask the following question: could dark matter be refuted? While all these discussions were going on, a new mind-blowing theory emerged. Our current models say that the universe began with a Big Bang, or rather, an extremely rapid inflation, and that inflation encompasses everything we see or cannot see now. However, the new paper raises a different possibility. According to Catherine Fries and Martin Wolfgang Winkler, two physicists at the University of Texas at Austin, who are the lead authors on this study, about a second dark Big Bang that occurred within a month of the first Big Bang in their still unpeer-reviewed work. These two physicists even go further, suggesting that their models could produce a range of exciting experimental signatures detectable by current and future devices, implying that direct testing of the dark Big Bang origin of dark matter may be possible. What's interesting, this wild new alternate cosmology could account for some of the most perplexing riddles about dark matter, which is about 5 times more abundant than the regular visible matter that makes up stars and planets, yet has still evaded direct detection. As Fries and Winkler said in their study, according to the cosmological standard model, the very early universe went through an epoch of inflation, a rapid expansion of space driven by vacuum energy. The origins of matter and radiation lie in the hot Big Bang, which terminates inflation and releases the vacuum energy into a hot plasma of particles. The latter contains the photons, leptons, and quarks of our visible universe, and, in the standard picture, also the dark matter. However, there is no genuine reason for a common origin of visible and dark matter beyond simplicity. Furthermore, despite excessive experimental searches over decades, no direct non-gravitational interactions between visible and dark matter have been detected. In this light, we will present an alternative cosmological scenario in which the visible and the dark matter sector are completely decoupled other than through gravity. The hot Big Bang only induces visible radiation and matter, but no dark matter at all. It's a mind-boggling new interpretation of our cosmic origins, But the researchers said the idea of a dark Big Bang does not appear to violate the constraints associated with models of early cosmic structure formation, provided that dark matter emerged within a few weeks of the birth of the universe. There are a number of possible scenarios that might lead to this 1-2 punch at the beginning of time, but Friese and Winkler focus on what's known as a first-order phase transition that led to the creation of dark matter. Essentially, in addition to producing the seeds of regular matter, the original Big Bang generated a dark quantum field that didn't immediately decay. As the days rolled by in the universe's infancy, regular matter cooled into atoms, a process known as Big Bang nucleosynthesis. At some point around the point of BBN, the dark quantum field did finally decay and transform its state, sparking the dark Big Bang that created dark matter. One of the most exciting implications of a dark Big Bang is that it would leave traces that could be potentially detectable to modern instruments. For instance, an event of this scale would probably produce gravitational waves, which are ripples in spacetime that might be observable in observations of ultra-dense stars known as pulsars. Indeed, Friese and Winkler suggest that a project known as the International Pulsar Timing Array may have already spotted potential evidence for a dark Big Bang. They said that the dark Big Bang phase transition generates strong gravitational radiation. We investigated the sensitivity of ongoing and upcoming pulsar timing array experiments to the gravitational wave signal from the dark Big Bang. We found that already the ongoing International Pulsar Timing Array run, which combines several individual pulsar timing array experiments, has an exciting discovery potential for dark Big Bangs, which occur around or after Big Bang nucleosynthesis. Intriguingly, a tentative gravitational wave signal by the nanograv experiment, included in the International Pulsar Timing Array network, could already be interpreted as the first sign of the dark Big Bang. Future instruments, such as the enormous square-kilometer array, could provide even more sensitivity to the search for signs of this speculative origin of dark matter. At this point, it's hard to predict whether this unusual explanation for dark matter might ever be backed up by hard evidence, but the new study provides a tantalizing roadmap to seek the answer to one of science's most intractable riddles. Hopefully, researchers will be able to confirm or disprove this idea within a few years. After all, being open to experimentation and observation, as well as thought-provoking. Otherwise, there are universes that we all dream of. However, only the provable ones in these universes are worth seeing and telling. Notably, as an important step in our endeavor to understand the formation of the Milky Way and other galaxies, scientists are building a better account of the lives of adolescent stars, starting from their births in collapsing clouds of cosmic gas and dust to the time they fly the nest and drift away from other young stars in their original clusters. Studying these stellar timelines will help scientists better determine the ages of stars, and because age is a fundamental parameter in astrophysics, it can ultimately offer astronomers a clearer picture of how star systems and even entire galaxies evolve. The team developed its new method of age determination by harnessing two of the most powerful and accurate techniques already employed by astronomers to study stars. They found that one, known as isochronous measurement, can be used to determine precisely when stars are born. The other, known as dynamical. Synchronizing these two differing cosmic clocks revealed to the team that stars snuggle up to their stellar siblings for around 5.5 million years after birth. Our work paves the way for future research into star formation and provides a clearer picture of how stars and star clusters evolve, Nuria Mirat-Roig, team leader and an astrophysicist at the University of Vienna, said in a statement. This is an important step in our endeavor to understand the formation of the Milky Way and other galaxies. Thus far, the best age approximations scientists have for stars apply to stellar bodies found in star clusters. which are most often of the same age because they formed from the same collapsing cloud of dust and gas. Miret-Roig and the team applied isochronous measurement and dynamical tracking to 6 relatively close star clusters up to 490 million light-years away. These clusters are also relatively young, at around just 50 million years old. They found isochronous measurement gave an age 5.5 million years older than dynamic backtracking. This indicates that the two measurement methods measure different things, Miret-Roig explained. The team theorizes this is because the isochronous measurement clock starts ticking when stars are born, while the dynamical backtracking clock only starts running when a star cluster expands and individual stars start to break free of their siblings, as well as the natal gas and dust clouds they were born in. This age difference between the two methods represents a new and much-needed tool to quantify the earliest stages in a star's life. Research co-author and professor at the University of Vienna scientist João Alves said, "Specifically, we can use it to measure how long the baby stars take before they leave their nest." The synchronization of these two cosmic clocks and the discovery that the embedded phase lasts around 5.5 million years was made possible with data from the European Space Agency Space Mission Gaia, which is currently building an extraordinarily precise three-dimensional map of more than 1 billion stars throughout our Milky Way galaxy. The results were also aided by radial velocity measurements of stars from the ground-based Apogee catalog. As Alves said, this finding has significant implications for our understanding of star formation and stellar evolution, including planet formation and the formation of galaxies, and opens up a new perspective on the chronology of star formation. For example, the length of the so-called embedded phase, during which baby stars remain within the parental gas cloud, can be estimated. Another new research has revealed that different types of neutron stars, born when massive stars die, behave in a similar way. This might sound like a minor result, but in the grand scheme of things, it's a finding that further supports the idea that these extreme dead stars, so dense a tablespoon of one equals something like the weight of Mount Everest, could be behind mysterious blasts of radiation called fast radio bursts. Millisecond-long bursts of radio emission. Fast radio bursts seem to come from sources beyond the limits of the Milky Way, yet since their discovery in 2007, their origins have remained shrouded in mystery. There is one possible suspect, however: highly magnetic neutron stars, or magnetars. And the team behind the new discovery, including researchers from the Max Planck Institute for Radio Astronomy and the University of Manchester, found that magnetars indeed share a relationship between the pulse structure and rotation that also present in other so-called radio-loud neutron stars. The discovery of a similar universal scaling between different sorts of neutron stars hints at the plasma processes that may be responsible for these radio emissions themselves. It also leads scientists to interpret structures seen in fast radio bursts as being the result of a corresponding rotational period. As Michael Kramer, first author of a paper on the findings and the director of the Max Planck Institute for Radio Astronomy, said in a statement, "When we set out to compare magnetar emission with that of fast radio bursts, we expected similarities. What we didn't expect is that all radio-loud neutron stars share this universal scaling. Neutron stars form when massive stars run out of fuel for nuclear fusion. Once a star runs out of such fuel, the energy that's been supporting them against the inward crushing force of their own gravity ceases to exist. This then causes the outer layers of the star to be blown away, resulting in massive supernova explosions while the core itself collapses. That collapse continues until electrons and protons in the region smash together and create a sea of neutron-rich matter, which prevents the stellar core from crushing down ever more. Any more, and the core would eventually create a black hole. Sans black hole, however, the result of the core collapse process is a body around the width of a city here on Earth, about 12 miles or 20 kilometers, and matter that's incomprehensibly dense. Recall the Mount Everest example. This isn't the only extreme quality the gravitational collapse causes, however. Just as an ice skater can speed up their spin by drawing in their arms, the stellar cores that create neutron stars reduce in radius and therefore spin up. This spin-up process can affect a core quite a bit. Some younger neutron stars, for instance, can rotate as fast as 700 times every single second. And, if they are, blasting out jets of radiation that sweeps over Earth like a beam from a cosmic lighthouse. The fast-spinning neutron star is called a pulsar. Neutron stars that rotate hundreds of times per second are called millisecond pulsars. The two pulsars are notable for their periodic nature. Rotating radio transients, on the other hand, are neutron stars that emit more sporadic and less well-timed blasts of radio waves. Additionally, when the magnetic field lines of stellar cores crush in during this collapse, magnetic fields that are 1,000 billion times stronger than the magnetic field of the Earth are created. But some neutron stars have more powerful magnetic fields than even that, pushing limits 1,000 times stronger than that of a normal neutron star. These are known as magnetars. Astronomers know of around 30 magnetars to date, and around 6 of those have been seen to emit radio waves, leading scientists to theorize that fast radio bursts come from magnetars outside the Milky Way, extragalactic magnetars. The team set about investigating the possible magnetar. Fast radio burst link by looking at individual pulses of the 6 known magnetars in detail. They then probed the substructure of the pulses with the radio telescope Effelsberg, located in Bad Münstereifel, Germany, one of the largest fully directable radio telescopes on Earth. To the team's surprise, the fast-rotating millisecond pulsars and rotating radio transients have similar pulse structures. This led them to a universal scaling relationship for magnetars and the other forms of neutron stars that connect pulse structure to the rotational period, whether these extreme stars are rotating every few milliseconds or in around 100 seconds. We expect magnetars to be powered by magnetic field energy, while the others are powered by their rotational energy, Kuo Liu, team member and a scientist at the Max Planck Institute for Radio Astronomy, said in the statement. Some are very old, some are very young, and yet all seem to follow this law. In other words, the fact that all these radio wave blasting neutron stars behave like magnetars suggests that the intrinsic origin of the subpulse structure must be the same for any and all neutron stars emitting radio waves. As Ben Sappers, team member and a researcher at the Jodrell Bank Center for Astrophysics, said, if at least some fast radio bursts originate from magnetars, the timescale of the substructure in the burst might then tell us the rotation period of the underlying magnet or source. If we find this periodicity in the data, this would be a milestone in explaining this type of fast radio bursts as radio sources. As a remarkable note, NASA's already testing tech for the next generation of Mars helicopter. The agency recently released a video showing a pair of Mars helicopter rotor blades getting tested at the agency's Jet Propulsion Laboratory. The test occurred on September 15th, just one day before NASA's Ingenuity helicopter made a record-breaking flight on the Red Planet. With Ingenuity's major success, NASA is planning to incorporate helicopter-like drones into future Mars missions too, built with designs more robust than their predecessor, which has completed 66 flights and counting. The new dual rotor system recently tested at Jet Propulsion Laboratory features 2 carbon fiber blades measuring more than 50 inches or 1.3 meters in diameter. That's nearly 4 inches or 10 centimeters longer than Ingenuity's are. The rotors were tested inside Jet Propulsion Laboratory's 25-foot space simulator, a vacuum chamber used by NASA engineers to expose spacecraft systems to conditions similar to those they will face during a mission. The stainless steel compartment spans 85 feet or 26 meters in height, and can simulate the conditions of extreme temperatures and solar radiation found in the vacuum of interplanetary space. Over the course of 3 weeks, the dual rotors were spun at exponentially greater speeds to test their durability. A NASA video from inside the space simulation chamber shows a SEP-15 test during which the blades are spun at Mach 0.95, which is nearly the speed of sound. Coincidentally, Ingenuity completed a record-breaking flight just the next day. On September 16, the Mars helicopter flew its 59th flight across the Martian surface, reaching an altitude of 66 feet or 20 meters. At the time, this marked its highest flight yet. However, that record was broken during an October 5 flight, during which Ingenuity flew to a height of 79 feet or 24 meters. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.